Hi everyone, welcome back to our channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have one of our students, Oscar, who did one of the courses for ROS Basics, and this one was in C++, and in which he will show us the final project of this course, in which he has to show us some programs on a real robot here, and so we're very excited to see what he's done. So hi Oscar, how are you doing?
Hey, how are you doing? I'm doing well. How about you?
I'm doing great as well. So I'm excited to see what you have here for us. So whenever you want, you can start sharing your screen and
Okay.
yeah, show us.
Okay, I will share your screen. So first of all, thank you for this. I found this your platform awesome to have this insights about where to start with ROS and keep on going through projects. So
I'm
I find it really nice.
I'm really happy to hear that.
So here I'm about to share my screen. I hope, let me know if you can see it.
I can see it.
Okay, so as you can see, I'm connected to the robot in remote.
Uh-huh.
And I have my terminal ready to launch the package I was working on, which is I called it Real Robot Lab underscore C++.
Mm-hmm.
So uh, so should I launch now?
Yes, let's see. So this is the whole project, right? This is the final sort of
Yeah,
behavior
of
that we're
course.
expecting. Yes, let's
It
see it.
takes into account how the robot, you will see it, how the robot prepares to align to the wall, do one lap around the arena, and stop and provide information about odometry.
Great.
So let's give it a try. Now everything has been launched.
Okay.
So first, as we may remember, we have the service server, which is in action. The first action that we can see is how the robot is trying to find the closest wall to get close to.
Okay, yeah, I see it rotating.
So here we have some feedback on the terminal, find it wall, real robot, and then now the current action is approaching the wall. And now the robot is, once he approached close enough, now is aligning to find a wall on its right side. I put very slow motion just to keep
Yeah, I like that. I like that.
the robot safe.
It can take a lot, but especially when you're debugging and things like that, it's definitely better to go slower.
Yeah, on the contrary, in the simulated robot, I put some a more speed.
Yeah.
Simulated robot, if it breaks, it's okay.
All right, and this feedback is from an action, I'm assuming.
Yeah, you're right. Now we have in parallel the wall following behavior, which is in action, and the action server, which is working, providing each second feedback of the current distance the robot has moved so far.
Okay. And here it's noticing it's getting too far away from the wall and kind of coming back. Yeah.
Yeah, it's uh, we can talk about the implementation of the wall following behavior.
Yes, why don't we do that because while this is running, go ahead and get started on, how you did separate it in sections and how you solved each section.
Yeah, actually, yeah, I like the word separation because for the implementation of each behavior, in this case, the wall following behavior,
Uh-huh.
I have, of course, one main client, but each time I created a class to embed the behavior. So this behavior is a simple one. I implemented if conditions,
Hmm.
comparing in priority if we have a frontal obstacle with the front distance. If this condition it's okay, that means that we don't have an obstacle. We keep going to compare if we're closer or further from the right wall.
Right.
So it's a series of 3 if conditions. For the purposes of this project, I decided to keep it like that in order to go further with the main goal, which is to create this ROS architecture with services and actions. And the interesting thing about this is that in the class in which I implemented the wall following behavior, I created an action client.
Right.
As we may remember from the course, the action client can get some status about the current status of the action server.
Yeah.
If it's ongoing, if it's pending. So as soon as the action client, the action server, keeps on going, that means keeps on going, recording odometry and providing this feedback, the wall following behavior keeps active.
Okay, right. So yes, that's the main benefit of
an
action.
Yeah. That's how I manage that aspect. So how do we know when the robot completed one lap? I did it experimentally by measuring the current distance the robot has moved. Let's say I put the robot to do some sport, to do some laps around the arena, and estimated a threshold about the more or less the distance that the robot needs to do in order to complete the lap.
Great, and we can see that it's completed the action, and yeah,
it has completed the action, and as we can see in the terminal, it's providing the final list of odometries that were being recorded each time.
Okay, nice. And that's just the result of the action?
Yes, that's the result
you're
of the
printing
action.
the result, or what are you printing there?
Okay, first, during the action was taking place, I was providing the feedback. The feedback of the current distance the robot has moved. Later on, when we can see that the threshold is around 5.7 meters. When the robot has completed one lap around the arena, then I provide the list of odometries that were being recorded during the action, the behavior was taking place.
Okay, and can we take a look just to, like, for example, the main node of your program that calls the servers and does the wall following, just to sort of
of course. I think that's a very interesting part, how the architecture of this project was implemented. So here we can see 3 CBP files. The most important one is this one, wall following client, because this is where everything is called. I will go lower to the main of this code. So here we have our main function. First of all, we are going to call, we create the node, and the first thing first, we will call the service. So here we have a basic service client implementation, and the service implementation, it's implemented in another file called find wall service server.
Okay, and why is that in an if with the line 281 to 295?
Okay, please don't mind the ifs. It was during the testing part.
Oh, okay.
Okay, it was just to avoid some blind code.
Yeah, I was just curious.
Yeah, please, sorry about that. Please don't mind the ifs.
Don't worry. So you call it, you make the client there, and then
yes,
you call it right before I
Yeah,
mean,
I
at the
can already.
beginning. Oh, okay, you call it right there, and then
Yeah,
where do you call the other one?
and then we jump directly to this part. Again, sorry about the if directives. In this part, this is a wall following class. So here, in the previous lines, we have the service part.
Uh-huh.
And here,
Oh, you
as
call
I
it
was mentioning
methods.
before,
Oh, that's nice. Yeah, yeah, yeah. You said that. That's nice.
in the wall following class, I have the action client. So we have the three actors of this part.
So the recording of the odometry then is sort of like a feature of your wall following class.
Yeah, kind
Nice.
of.
All right. And then the logic is just if it's more than 3 centimeters, whatever, turn right. It was like you didn't apply like a PID or anything. It was just like a simple if-else statement for the movement, correct?
Yeah, if I may go to this part, yeah,
Because right
here we
there.
got it.
Yeah, okay. Just three
Yeah, it's
scenarios. Okay, great. And then you said you did experimentally to know how long the track was to stop everything.
yeah, this is an interesting part. If I may go to this odometry part.
Yeah.
So this in this code, we are in the action part, in the action server. So it requires an action class, an action related class. But however, I created what I called a recorder class.
Mm-hmm.
This is a class that will take in charge the data acquisition, the construction of the odometry vector. So in the action class, we can just care about distance calculation and storing of the odometries. This recorder class will have some methods like, as I was saying, data acquisition in the odometry ROS type data. We will have the transformation from quaternion to Euler angles in order to build our odometry vector as requested in the guidelines. And finally, we have our method called record odometry, which will retrieve the X and Y position plus the orientation in the Z angle, in the Z axis.
All right.
I found it really interesting to split this recorder part in order to make it more readable.
Yeah, like that's what I was gonna say. It's very organized, very simple, and great commenting. It's always nice to see. But yeah, it's a nice way to separate it. I like it. And just to sort of finish my questions here. Oh, just one comment.
Of course.
Noticed, I don't know if you misspoke, but I just want to make sure, since we're doing like the basics course, to have these concepts clearly. And you said that in the beginning, you said that the service server provides an action. I was going to say, I'm pretty sure you meant it provides a service, right? Just to separate those two things, like an action server and a service server.
Yeah, sorry about that. I was a little bit redundant on my vocabulary.
Right.
But I mean,
but then you explained it. Yeah. Then you explained it and why an action why you should use an action, for example, for this odometry recording.
I mean, if I employed the correct words, the service server was providing a service and the action server was providing an action service. But yeah, of course, service, it's a blocking operation, and action, it's not blocking operation, which allows to
that's the main thing.
Record odometry.
Yeah, okay, good. And then just the last question I have is, how does the service server find the wall, and what happens if you're closer to an obstacle?
Okay, for the first question, I employed the following approach. I actually prepared a drawing to clear it up. I don't know if you can see it more or less.
I can't see your screen right now. I can.
You can see my camera.
I can see the just the window of the IDE.
Okay, I should stop sharing just for a moment.
Yeah.
Mm, okay, great. Sorry about that. I
No, don't worry, don't worry.
so I guess you can see now
Uh-huh.
some diagram.
I see it. Yes. Yes, I do.
So regarding for your question, how did I found a wall? How the service found a wall? So let's take this is a robot. This is a robot,
All
and
right.
this is the front axis of the robot. So basically, what I did is to take it's a random number, but it worked kind of quite well.
Yeah.
8 samples of distance measurements from one side, and 8 samples of distance measurements to the other side.
Okay.
These distance measurements, I projected them on the central axis. Of course, I estimated the angle in between each ray to the central axis.
Mm-hmm.
Once the projection was done, I this is kind of a zoom to this part. Once the projection was done, I estimated the standard deviation of these projections. If let's say in an ideal world, this projection should be the same, no difference. Mm-hmm. But of course, here we have some noise normally with sensors. And I defined a threshold for the standard deviation in order to let me know, okay, now all the projections are more or less the same. So we can assume that we are facing the wall.
I understand. Okay. Yeah. Oh, nice. With the standard deviation.
Yeah.
So then this allows you to know if it's not if it's something shorter, correct?
Yeah, of course, I added a filter to not take into account further walls, let's say. Just to take into account close by walls, because I don't want it to align to a wall which is further from the starting point.
Okay. All right.
So yeah, this is the main strategy for the wall finding algorithm. That's for your first question. And let's say if we have an obstacle in this field of view, I didn't test it, but I would imagine that if we have an obstacle inside here, the standard deviation will be just big regarding the projections, because we will have some measurements,
Right.
big measurements, and some
longer.
close by measurements.
The standard deviation will be a lot longer. Oh, that's really
Yeah.
really nice. And that's also not asked in the project. I was just curious how if you had done it. That's great.
Yes, I remember in the last presentation with Python, I employed a different approach. I don't remember exactly but it was about not looking at certain indexes of the certain parts of the leader, but with this approach, you can actually simplify the amount of data you're looking at. You're looking at let's say at most 16 samples of data measurements.
Wow. So
that you can take into account whenever the standard deviation of the projections is kind of short. You can tune that threshold in order to identify the wall.
Awesome. Well, those all the questions I have for you, Oscar. Congratulations, really clear, really clear project, and I like that you went a step ahead in both the wall following. I'm sorry, the wall finder with this what I just asked, and also the separation of the odometry recording classes. I thought that was really nice too. So congratulations, Oscar. It's really nice project.
Thank you.
And yeah, for everyone else that is watching, you can do this here. What Oscar did for his course, you can come to our platform and take our course, and then to sort of certify your knowledge, we do these presentations with the real robots. So I invite everyone to do it like Oscar has done here. And Oscar, again, thank you very much for your time and for your presentation.
Thank you. Thanks to you.
All right, guys. So that's it for us. So we'll see you guys next time for our next video. All right, bye. Bye bye.
Bye bye.